This is my second video for Unit 5C, Intramolecular Forces. In this video, we'll be determining the polarity of a molecule. So go to page 6 in the class packet. Motivation. Which shape below is symmetrical and how do you know that? Take a moment to analyze it. Learning target. At the end of the lesson, I'll be able to determine if a molecule is polar or nonpolar by applying symmetry rules. For announcements, you could do homework number 2, which is a journal plot based off this lesson. For nonpolar molecules, they have a symmetrical distribution of charge or atoms. So how does this happen? The dipole arrows within the molecule cancel out. On the regions, if your molecule or atom have both vertical and horizontal symmetry, it is considered nonpolar. For example, here we have a circle. It has both horizontal and vertical symmetry. Here's an example of dipole arrows canceling out. If two dipole arrows are the same magnitude, which means the same size, and they're facing opposite directions, they will cancel out. Here's one that's facing top, and this one's facing bottom. They will cancel out. If all the dipole arrows cancel out, your molecule is considered nonpolar. Polar molecules have an asymmetrical distribution of charge or atoms. So the dipole arrows do not cancel out. On the regions, if you're given a molecule that is not symmetrical by both vertical and horizontal symmetry, it is considered polar. If your molecule only has vertical symmetry but not horizontal symmetry, it is still considered polar. For example, with this shape, it has vertical symmetry but not horizontal. So this will be considered polar. This is the same if it only has horizontal symmetry but not vertical. On the regions, it must have both vertical and horizontal to be considered nonpolar. If it just has one but not the other, it is not symmetrical and is considered polar. Here's an example of the dipole arrows not canceling out. Notice that even though both dipole arrows are the same magnitude, they're not facing in opposite directions, therefore they do not cancel out. Most of the time when people talk about polar molecules, they mean polar covalent molecules and not ionic compounds. Dipoles are vectors. Vectors is a quantity that has both magnitude and direction. If we look at this dipole arrow, the size of the arrow represents the magnitude and it faces a certain direction. Let's compare these two bonds, Fs bond and SCl bond. To determine which bond is more polar, we need to calculate the electronegativity difference using table S on your reference table. Since Fs has a larger electronegativity difference than SCl, it is more polar. Therefore, the dipole in Fs bond will be larger than SCl bond. The more polar the bond, the larger the dipole. Notice that the dipole arrow faces the more electronegative atom. The end of the dipole arrow faces the less electronegative atom. The dipole arrow points towards the more electronegative atom to show there's increased electron density because the more electronegative atom has a higher attraction for the bonding electrons. Let's look at this molecule and use the dipole arrows to determine if the molecule is polar or not. If the molecule is nonpolar, the dipole arrows will cancel out. If the molecule is polar, the dipole arrows will not cancel out. So after we draw the dipole arrows, notice that one of the arrows is much larger than the other one. Even though they're facing opposite directions, they will not cancel out. If you were to combine both arrows, you get a net dipole. And since there's a net dipole, this molecule is polar. Now we're going to do a small activity to figure out if the following dipoles cancel out. So this will be based off the geometry from this table. In each of these examples, we're assuming the dipole arrows are the same size. So same magnitude, same type of bond. The first example is two dipole arrows with the same magnitude facing opposite directions. Remember, each dipole represents a polar bond. The shape of this is linear. The angle between the two dipole arrows is 180 degrees. Do these two dipoles cancel out? Yes. If your molecule have a linear shape with two bonds that have the same electronegativity difference, that molecule is considered nonpolar because the dipoles cancel out, and there is no net dipole. Here we have two dipoles that are 90 degrees from each other. Do they cancel out? They do not, because they're not facing in opposite directions. In this situation, the dipole arrows are 105 degrees from each other. In a molecule, this is considered a bent shape. Do the dipole arrows cancel out? The answer is no, so our molecules with a bent shape are considered polar. In this situation, we have three dipole arrows. This represents a trigonal planar shape. Each dipole arrow is 120 degrees from each other. Do the dipoles cancel out? These dipoles do cancel out. Why is that? If you were to draw the net dipole of these two arrows, notice that this dipole, that is the net dipole of these two arrows, is the opposite direction of this dipole over here at the same magnitude. So these two arrows will cancel out. As a result, molecules with a trigonal planar shape are considered nonpolar because the dipole arrows will cancel out. In this situation, we have four dipole arrows, which represents a tetrahedral shape. So each dipole arrow is 109.5 degrees from each other. Do the dipole arrows cancel out? Yes, they do. It might be hard to tell from looking at this diagram since it's not exactly 3D, but if you were to put this diagram in a cube, you can clearly see that the dipole arrows will cancel out. Molecules with a tetrahedral shape with the same size dipole arrows are considered nonpolar. In this situation, we have a trigonal bipyramidal shape. There's two angles, 90 degrees and 120 degrees. So do the dipoles cancel out for trigonal bipyramidal? The answer is yes. Here's a 3D picture of trigonal pyramidal. There's two pyramids, one on top, one on bottom. If you look at the trigonal pyramidal shape, it is a combination of the linear and trigonal planar shape. From top to bottom, that's the linear, and the middle part is the trigonal planar shape. So we already know dipoles in linear and trigonal planar shapes cancel out. So dipole in the trigonal bipyramidal shape will cancel out. So molecules with a trigonal bipyramidal shape with the same size dipoles are considered nonpolar. In our last example, we have an octahedral shape in which the dipole arrows are 90 degrees from each other. Do these dipole arrows cancel out? Yes, they do. So molecules with an octahedral shape with the same size dipoles are considered nonpolar. So just to summarize, if a molecule has symmetrical charge distribution, it's considered nonpolar. If a molecule has asymmetrical charge distribution, it's considered polar. One way to help you memorize this is SNAP, symmetrical nonpolar, asymmetrical polar. To determine if a molecule has symmetry, there's two ways to do it. On the regions, you can check if the molecule have both horizontal and vertical symmetry. The better way to do it is to look at the shape and geometry and check if the dipoles cancel out. Let's do a couple examples. Let's look at carbon dioxide. Is this molecule polar or nonpolar? So I'm going to use the two methods. The first method you can use on the reagents is basically checking if there's horizontal and vertical symmetry. As you can see, carbon dioxide has both vertical and horizontal symmetry. Therefore, it is symmetrical and therefore it is considered nonpolar. The second method is checking if the dipole arrows cancel out. So carbon dioxide have a linear shape. As you can see, the CO bond is a polar bond, and since we have two of them, we have two dipoles. Since carbon dioxide is a linear compound, the dipoles are facing in opposite directions, therefore they will cancel out, and since they cancel out, CO2 is considered a nonpolar compound. You can use either method on the reagents, although the second method involving checking if the dipole canceling out is a better method. Let's do another example. Is water polar or nonpolar? On the regions, the only shape you need to know is water. Water has a bent shape. In case you ever forget, it's the same shape as Mickey Mouse head. So we're going to use the two methods again. Does water have both vertical and horizontal symmetry? As it turns out, it only has vertical, but not horizontal. Therefore, it's considered polar. In order for it to consider be nonpolar, it needs to have both vertical and horizontal symmetry. If it just has one, but not the other, it is considered polar. If we use the other method, we have to draw the dipole arrows. Since OH is a polar bond, we draw the two dipole arrows As you can see, the two dipole arrows do not cancel out. Therefore, water is a polar molecule. Learning check number 1. Given the formula representing a molecule, which statement explains why the molecule is nonpolar? Pause the video and resume once you complete it. So the answer is 3. Remember, SNAP. Symmetrical nonpolar, asymmetrical polar. If it's nonpolar, then it must be symmetrical in charge distribution. Learning check number 2. Which formula represents two polar molecules? Pause the video and resume once you complete it. We know that CO2 is a nonpolar molecule, so 1 and 2 are wrong. We know water is polar, so we just need to check HCl and CH4. For HCl, notice it does not have any vertical symmetry. The left and right side are different from each other. Therefore, HCl is a polar molecule because it does not have both vertical and horizontal symmetry. So the answer is choice 3. If you were to draw CH4 geometrically, notice it has both vertical and horizontal symmetry. Therefore, CH4 is a nonpolar molecule. Learning check number 3. Which formula represents a nonpolar molecule containing polar covalent bonds? Pause the video and resume once you complete it. The first step is to check if the following are nonpolar molecules. We know 4 is a polar molecule, so that's wrong. For number 3, we check the horizontal and vertical symmetry. As you can see, it does not have any horizontal symmetry. Therefore, 3 is a polar molecule, so that's also wrong. For choice 1 and 2, 1 has horizontal and vertical symmetry, so it is nonpolar. And number 2 also has vertical and horizontal symmetry, so therefore it is also nonpolar. In the question, it also states that this molecule must also contain polar covalent bonds. We know H and H is nonpolar because they're the same element. If we look on table S on the reference table, C-F bond is polar, therefore the answer is choice 2. On the regions, you can draw the shape of the molecules as geometric as possible except water. So that will help you determine if the molecule is polar or nonpolar using horizontal and vertical symmetry. Now I want you to determine if the following statement is true or false. Molecule can be nonpolar even though it has polar bonds. Take a moment to think about it. So the answer is true. An example of this will be carbon dioxide. Notice it has polar bonds. CO is a polar bond, is a dipole, but the molecule itself is nonpolar because it has vertical and horizontal symmetry and the dipoles cancel out. Here's another statement. Molecule can be polar even though it has nonpolar bonds. Take a moment to think about it. So this is also a true statement. An example of this will be ozone. So ozone is a polar molecule even though it has nonpolar bonds. So OO, which is the same element, this is a nonpolar bond, but the molecule itself is polar. The molecule is polar because of this bent shape. So you notice it does not have any horizontal or vertical symmetry. The reason why the molecule is bent is because of the lone pairs. If you were to draw the resonance structure and write in the formal charges, you can see that the middle oxygen has a positive formal charge and the other two oxygens have a negative formal charge. Therefore, there are two dipoles and they do not cancel out because of the bent shape. Therefore, ozone is a polar molecule. In summary, the polarity in the bond is determined by the electroactivity difference in table S. The polarity in molecule is determined by the shape of the molecule, whether they have symmetry in charge distribution or not. So keep in mind that there may be situations in which a nonpolar molecule might have polar bonds or a polar molecule might have nonpolar bonds. In this practice, I want you to complete the following table. You may need to draw the Lewis dot diagram for some of these questions, for example, CH3Cl, but keep in mind the Lewis dot diagrams are from the previous packet. Some compounds may have both polar and nonpolar bonds. So remember to indicate them. So determine if the molecule have polar or nonpolar bonds or both. If it's symmetrical, yes or no. and if it's a polar or nonpolar molecule. So pause the video and resume once you completed the table. Okay, so here's the answers. So notice that CH3Cl have both nonpolar and polar bonds, but since it's not symmetrical, it is considered polar. Here are the answers for the next part of the table. So this concludes the video lesson for today. Remember to do the Junipod homework.